Today's session, we'll be talking about time series data analysis. And for that, I have already shared one synthetic data set on patient monitoring with all of you. I hope all of you have received it on WhatsApp group. I'll be sharing my screen with all of you to start with time series analysis today. When we are talking about time series analysis, it is slightly different from the normal regression and classification modeling that you have done earlier. So this is little advanced one technique we are learning here that generally goes for data sets where you are trying to observe possible future trends in certain set of observations. Like maybe for patient conditions, it may be predicting future variations in the heart rate, or maybe predicting something relevant to health parameter of patient, so that some early warning systems can be designed and it can lead to support for the patient health, like maybe in ICUs or in emergency units. We can have a timely alert system if the system finds some sudden discrepancies or critical change in patient parameters. So we can automate those processes. So with that mindset, generally the time series analysis is required. Because here I'm talking about time series, that means in your data, time is one of the important factor that is required. Means the samples that are collected, they should be available with a continuous sampling period. They should not be like some random samples. Rather, with a regular pattern, they should be captured so that they present a continuous time series, like maybe a weekly monitoring on patient or monthly monitoring continuously that we are doing on the patient in ICU. Based on that trend only, we can predict something. So this is different in comparison to the normal supervised case studies that we have conducted in past 2 days. So for time series data analysis and forecasting, your data should be based on those key criteria. So it should have timestamp and it should have continuous set of observations for relevant parameter that you want to predict. Few things that are related to the initial libraries and data loading process, they will be common in this case study also. But after that, we'll be focusing on seasonal patterns, trends in your data, and based on that, a new statistical model will build for the prediction purpose. So starting with the very first step that you already know, we will just need some libraries here. So I'll write import libraries, and they will be same libraries initially. After doing initial analysis, I'll be using specialized libraries for seasonality or trend analysis. That will be based on stats model. There is a separate library called stats model in Python that we can use for trend analysis or for statistical analysis specifically. So I'm writing here import pandas as PD, then import numpy as NP. Further, we'll import matplotlib.pyplot as PLT, and then we will import Seaborn as SNS. So these 4 libraries, all of you need to get ready, and I'm sharing this code in your code share window also. Execute this and get all your libraries ready. If you get any trouble, post in the chat box. I'll be here to help. In the next step further, we will load dataset. And dataset, as you all know, we have that synthetic healthcare time series data.csv file that we'll be taking. So I'm creating a variable df. Df generally we use to indicate data frame. So you can take any variable. It can be data variable, it can be df variable, or any other name you can give. So I'm giving just a quick name df over here. Then I'm reading the CSV file. And inside this, as you know, we need to put address of your data file. So for this, we first need to put our data file in the files section, as we do every day. So I'll go to the files section here. Then I'll upload the specific data file. So I have it right here and click OK for any kind of warnings. And we'll wait for a while as this data gets uploaded. So this is now available here, and we can right click on this, we can copy path, and we can paste this path in the dedicated section. And then we are ready to run data head. So you can observe this is the current structure of our data. This is the important variable for time series analysis. This shows the continuous monitoring, like this synthetic data set is generated from January 2024 to few readings for a longer duration. And there are 5-minute samples, you can see. In every 5 minutes, a sample is collected. And in general, if you want to do maybe simple regression analysis or classification analysis, for that also there are some variables, like if BP you want to predict, that could be regression analysis. If health status you want to predict, for that also a specific parameter is there. But currently our target is to proceed with seasonality, means trend seen over time, like when we are observing patient over time, so how his health is varying, it is deteriorating or it is improving, that track we are finding. And we will try to predict heart rate with reference to time parameter. So we'll just analyze trend for heart rate right now. Otherwise, you have many other parameters also in this data. Later on, you can do analysis for them also. That is up to you how you want to analyze at different levels for your unique set of variables. So I'm sharing this data loading code also in your code share window. Let me know when you all are ready with this data on your screen. Let me know quickly in the chat box, then I'll proceed further. Thanks for the update. I hope others are also able to do the same. So I'm running info function after this, and here we can observe that there are 20,160 entries right now in our data with 9 different columns. And this one is important. The timestamp right now is in the form of object entry. But in Python, when we are working on time series data, this timestamp should be in a specific format. We call that date time format. That is a standard format that is required for timestamp, so that we can use it for trend analysis. So we need it to be in required format. And for that, I'll just convert this particular variable from object to date time, so that we get it in required format to proceed further with time series analysis. And for this, I'll take step further. That will be to convert timestamp. This will be our next step. And here I'll just choose my timestamp parameter. And inside this, I'll pass to date time. And inside this, we need to mention which parameter we are changing. So observe here what we are doing. I'm just converting timestamp to date time with the help of pandas, and the results will be stored in the same timestamp variable. So I'll run this. I can see the green tick mark here. And after this, if you try to run the info function again, you will see the updated version in your data. Observe, now this is in required format. Now this is in date time format, which is required when we are conducting time series analysis. Conduct this analysis and let me know when you are done with the conversion. Let me know when you are done up to this. Okay, great. I can see a response from one person, I guess. I suppose others are also doing the same if anyone is executing side by side. If anyone is stuck anywhere, they can let me know in the chat box quickly. Then only I'll be able to help. So next step I'm doing here, set timestamp as index column. Currently, you have observed here that in this data, this timestamp is also appearing like remaining features. This is like a normal parameter, means in Excel sheet, one normal column is held by this timestamp. But when we are doing a time series analysis, we don't need this as a column specifically here. Rather, we need to this to work as an index parameter. Index you can consider like these serial numbers are currently index values 0, 1, 2, 3. They are currently index values. By default, they are index value. But now we will make this timestamp as index. So that will be appearing more like a serial number. So timestamp will be creating that effect of continuous observations while staying in your serial number section. So what I'll do is I'm converting timestamp into index column. So I'm writing here df set index, and inside this I'll write timestamp. I'll make it in place is equal to true and df head. Observe, I'm introducing one new thing over here. This in place is equal to true. There are two ways to change. Observe this very carefully. Till now, whenever I make a change, I write equal to and then I make change into respective variable. So whenever we are executing something, we are writing it with equal to. But there are some functions that allow you to make change to the same variable without equal to. You need not to write equal to, you can use in place true. Means whatever changes happen to this timestamp after execution of this code, they get saved automatically in DF. The other way to write this is DF is equal to the set of code. This is same thing, and the one I'm doing right now, this is also the same thing. So just some alternative options only I'm showing you that because sometimes if you do extended coding, you may need to know some alternatives also. When maybe you don't want to save separately in a variable, you can just use in place true and that will work on the same section. So now you can observe timestamp doesn't appear like a normal column now. Rather, it is appearing slightly below in comparison to these columns. And this is working like an index column right now because we have set it as an index in our data. So I'm sharing this section of code also in your code share window. You can execute this. Let me know if you are able to see your data something like this. Okay, great. So now next step I'll do here, check patient counts. I'll just observe how many patients are involved in this particular data set first of all. So let me check this patient ID sequence available in our data. So I'll write here df patient ID and value counts, for example. And we can observe that it includes information on 10 patients. You can see 10 patients, and each patient contains 2016 observations. So per patient, these number of observations are present in our case. because this is a synthetic data, we are having equal number of observations in all patient categories. When you are collecting real patient data, maybe you will have different also. Like maybe if some patients are in your medical emergency or in ICU for a longer time, there may be longer observations. For others, there may be shorter observations. So accordingly, you may have to make decisions further. But since this is a synthetic data set, we can have a very balanced observation over here. So when we are working on time series analysis, there is no purpose of including all patients in one go, because time series forecasting is like you are predicting heart rate condition for a patient. So you will be doing analysis for one patient at a time, not all the patient, because you cannot predict heart rate of all patients all at the same time in time series analysis, because you are monitoring it with consistent observations from single patient at a time. So the system will be deployed patient wise, not for entire data. So what we will do is we will focus on maybe one patient for now. Later on, you can evaluate it for other patients also with some other type of data. You can connect that, or from here also the other patients you can evaluate. So let us do it for single patient at a time, and I'll take only the first patient. So I'll write here focus on one patient. This one I'll share. All of you can check this in the meanwhile. So while focusing on one patient, so I'll create a new data file. I'm calling it patient underscore DF, a new data file I'm creating that will involve entry for one patient only. So I'm writing here DF patient ID variable is equal to 1. Means wherever patient ID is equal to 1, only those observations I want to include in this new data set. This is what we are doing here. Here I am adding a control that wherever patient ID is 1, like this value is 1, this you can see, only those observations must be included in this new data. So it will just extract those 2016 observations for patient 1 only here. And we can even visualize that. We can see shape of patient DF. Now you can see only 2016 observations and all variables are present in this. So in this way, we are extracting only single patient data from available big structure of your data. Execute this, and then we will do further analysis. Okay, great. I hope others are also able to understand up to this. In the next step, I'll write here the resampling and signal smoothing task we are doing now. Now observe what we are doing in this data. This, since we have observed it with reference to the timestamps earlier, and we have observed that we are calculating samples in every 5-10 seconds here. But because these samples are generally calculated with some kind of sensors or maybe some equipments you have in your medical facility, so from there we are getting samples. But in actual, when we are building some machine learning model, or especially when it is IoT data, so IoT data is generally noisy. It is generally considered that there are some noise also because your sensors are not 100% accurate. So what we do here, instead of including all these measurements, we do averaging, like maybe 1 hour average, or maybe half an hour average, or maybe 15-minute average. There could be different scenarios that depends on your domain expertise. So currently we will consider just one scenario here. Like I'm doing just resampling and signal smoothing, considering that there may be some noise in our data and we have so many repeated observations, like in every 5 seconds, maybe there are no major changes in patient parameters, like we need some long-term averages. So for that, I'm creating here one smoothing by using 15-minute averaging sequence. So from every 5-minute data, I'll be just calculating 15-minute average. Like mean we will be calculating so that we process that information instead of considering all spikes. So this helps us to preserve trend instead of noise, so that if you, even you can do it for hourly averaging or longer averaging also, depending upon your domain requirement. So we can write here are 15-minute. I'm creating one new variable that is based on heart rate for 15 minutes, because I told you right in the beginning that we are going to measure this particular parameter. So I'm going to resample based on this heart rate. And I'll write here HR for 15-minute sampling we are creating. And I'm mentioning here patient DF data because this is the recent data we have created. Now we are working on this patient DF data. And inside this, I'll select heart rate parameter. Then I'll resample this with 15-minute average. So I'll write mean. So we are just resampling it with 15-minute mean, and a new data will be created based on that. We can even observe that data. Like I can write here 15-minute mean, whatever outcome we are getting based on this. So you can see this new variable we are creating now. I'm just focusing on heart rate and timestamp, and now you can see 15-minute sample it has created now instead of those 5-minute samples. So we have just averaged our data for 15-minute sequence. And I'm sharing this set of code also in your code share window. Execute this and we can plot this data easily now. Maybe if we want to see the trend out of this data, although because this is not a real time data, so there may be like a very normal flow of data you will see, but although that is not possible with the real patient data, but still you can understand the way to plot. Like even if you get a real data from somewhere, that will be also plotted in the same manner, but just the plot will be looking different. So we are doing it for 15 hour average. And figure size, I'm keeping, for example, 10,4. So we are just plotting this heart rate 15-minute with this description. And I'll run this and we can observe this is the current structure of this heart rate data we are having. Like just a normal flow, because this is created with synthetic details, so there are few anomalies also added, because this synthetic data, when I created this synthetic data, I have introduced some anomalies also into this, anomalies like noisy observations, to create a practical impact. So you can see that there are some anomalies that are taking it to the peak, and then this is just to make it look like a realistic data only. We have created this kind of a pattern that looks like in a specific format, along with some peak observations. So this kind of pattern you can observe from this simple code that I'm sharing for 15-minute plotting. Execute this and let me know if this is working fine. Yes, labels, etc. you can add. That you can do. Like currently, this is showing just your beats. So title in this plot we have updated. Let me check if we can plot it with Y label. So you can see a count I have added as Y label over here. You can change whatever you want to write. Accordingly, you can update this. I hope we are all good up to this. So now in the next step, I'm adding here for time series analysis and to judge trend and seasonality. These keywords are very important when we are dealing in time series data, because time series is all about trend prediction. What is happening in current observation scale, how it may change with time, like trend and seasonality. Most commonly, a simple example you can take in stock market prediction. In stock market prediction, this trend and seasonality analysis plays a very important role because it can help people to predict how the stock may change with some time. And this goes in many other areas also, like in patient monitoring, also for real time updates on how the changes may affect his health in maybe next 15 minutes or maybe next 10 minutes, so that timely assessment can be done. And if any treatment is to be updated accordingly, that season can be made ahead of time. Plot code I have shared in the code share window. I hope you can get it from there. Let me know if it is fine. So I'll do one more statistical analysis here. We will calculate rolling mean and rolling standard deviation for this particular herd data. Like the 15-minute data we have already extracted, we'll now conduct a rolling mean on this. So last time the mean we have calculated was strictly with 15-minute time sample. Now we are conducting rolling mean. If anyone needs a proper justification of what we are doing in that case, let me just show you quickly on whiteboard. While analyzing trends of something, we generally prefer to go with rolling mean in that case. So in this process, like earlier, we had a number of samples available in your data. So something like this, maybe these kind of observations you are having. So earlier we were having 15-minute cutoff. So maybe something like this, 15-minute, if this is on time axis. Then something like this for 15 minutes we'll have a cutoff. And then we will calculate first mean from here, second mean from here, third mean here and here, and so on. In this way, all the means will be calculated. So the updated data is based on these new mean values only. And we are just calculating from these proportions in a strict order only. When I'm talking about rolling mean, the pattern will be different. What we will do here, if you have data something like this time we will not do strict cutoff. Rather, we will start with a window size of like maybe 8 samples or maybe 10 samples or maybe 4 samples, for example. And this I'll make maybe, we call it 8 sample window. So in this sample, we are covering 8 samples. Then in rolling mean, we will keep on shifting this window by 1 sample ahead. This way, we will keep on shifting this so that this is continuously calculating mean one by one. 8 samples every time it will be covering by shifting either by 1 sample, 2 sample, those kind of control variables further you can update. Currently, I'm putting it in default form only, like covering 8 samples at a time and calculating mean continuously as the data flows further. So when continuous data from patient variables are coming, like when patient is in ICU or in emergency or maybe ward, and we are monitoring continuously. So we are continuously calculating mean as the data points are coming, and we are just shifting this window next to next to cover entire sequence of data, and this way we are just observing it continuously for the statistical evaluation. So we can calculate mean also like this, and we can calculate standard deviation also like this. Both these help us to analyze trend of or variability in your heart rate data. These are some of the most common statistical parameters that you can measure here. So for this, we will add here a simple sequence. First, I'll calculate rolling mean, for example. I'll write here HR 15-minute data that only we are using, for example, and I'm using here rolling function is by default available, and inside this I'll pass a window size of 8, for instance, and for this we'll be calculating mean. So a rolling window I'm creating, and as the window rolls on we will be calculating mean out of that. In the similar pattern, I can calculate standard deviation. So here also I'll pass rolling mean, then window 8, and here I'll write standard deviation. So both of these we are updating. We are just calculating these values directly here. I'll run this. Currently, we are doing this with already available data file, but this becomes very useful when real-time data is coming, because continuously you are able to evaluate that data as window keep on rolling over new set of samples that are coming from sensors or maybe from patient monitoring equipments, etc. So there it becomes more relevant, but currently since we don't have live data, we are using it on existing data only. So there also we can calculate this rolling mean continuously. Now I can plot this rolling mean just to observe how the variations are going on in data. So although this will be almost similar to what we have done earlier, that was your 15-hour data plot, but still we can just observe these things side by side. So we'll write here figure, and I'll pass here figure size 10 cross 4. Then I'll write here plot. So the first plot I'm doing is on original data, 15-hour data, and I'll mark here heart rate because this is name of this data in our uh, pattern. So we'll have this with label heart rate. The second plot I'm creating on the same graph is rolling mean. This observation that we have observed, a plot for that I'm creating. So I'll give it a name, rolling mean itself. Then one more plot on the same graph I'm creating that will be rolling standard deviation, and label for this again I'll keep as rolling STD. So these three plots will be creating, and we will have legend also side by side for each one of them so that the color coding can be done automatically in the system. And here we will pass title stating that we are measuring it for trend and variability in heart rate, and we'll just show this plot ultimately. So I'm running this, and you can observe these things we are having in the output. So the blue one is original heart rate, orange one represent its rolling mean. So you can see the spikes or the noisy observations will be better handled by this rolling mean, and then standard deviation that will be on lower scale generally. So that is also appearing here. So this will help you to understand what are the possible variations in your data. Like you can observe some peaks are unreachable in these positions currently. So this kind of trend you can observe from here quickly. So I'll be sharing this with all of you. You can execute the same. Rolling mean I have already shared. The figure information I'm sharing here. All of you can execute this and let me know when you are done with this kind of graph. And you can see on the x-axis, it is automatically taking the time factor now. So daily date, basically, it is updating automatically here. Let me know when you are done up to this. Okay, great. So I'll take it one step further, and now we will conduct a stationarity check on data. This stationarity check basically help us to decide about which prediction model we should use for this kind of data. Like if your data is stationary in nature, then we can consider a different plotting technique, so forecasting technique. And if your data is non-stationary in nature, then there may be a different modeling technique used for that. So we will use like a statistical evaluation over here to check stationarity of your available data set. And this basically helps us to understand how your data is varying, and how its mean, variance, and autocorrelation is varying over time, whether they are constant or whether they are changing. So if they are constant over time, means there is no specific trend in your data, then we call it a stationary data. However, in case of non-stationarity, your patterns will have heavy change with time. There will be many peak observation fluctuations with time. So that becomes non-stationary data. Are we doing copy paste? But at the end, kindly review what we have done because we are new to this. Okay, if it feels fast, you can always interrupt me in between. That is why right from the beginning, I'm asking time and again whether it is done or not. So you can always say that I have to wait for your execution or I need to repeat anything. That is why I keep on asking after executing everything. Every time you can let me know that I have to wait or I have to explain anything again. So for stationarity check right now, I'll be taking help from stats model. This is another library now we are taking. Stats model time series library I'm using here. And inside this, we will have a stat tools repository itself, from where I'm just taking add fuller test. This add fuller test will quickly help us to evaluate statistical information from our data. That includes ADF statistic test as well as p-value test. So both of them will help us analyze that how well the stationarity is going on in your test. That is especially for the time series analysis to check whether the series is stationary or not. So both of them will be executing here side by side. I'll write ADF result and I'll write here add fuller function. Inside this, I'll pass our 15-minute dot dropna. So this dropna is just a safe way to execute, so that if there are any kind of missing values in your data, they can be dropped during this analysis. Generally, we do not pass any kind of variable that has missing value. Although our data set right now is clean, but for safety purpose, we pass this dropna function along with variable, so that even if any missing values exist somewhere, they can be dropped automatically and a continuous data can be found, because in time series continuity of data is more important. Then we will use here the print sequence. ADF statistics we are following here, and that I'll be getting from ADF result. So the first outcome from this ADF result is this ADF statistics. That becomes your first. ADF here is augmented Ducky-Fuller test basically. And in general, as a beginner, if anyone has not executed this any time earlier, you can simply consider it like a test to check whether your data is stationary or not. Like if mean variance are constant over time or not. For that purpose only, we use this ADF statistics. So this generally provides two outcome. First outcome I'm taking from place 0, that is ADF statistics. And second value will be your P value. That is probably the most common value that all of you might have used during your statistical analysis. So second value I'm taking is P value. And here I'll pass result from 1 because this contains two positions of result. First position is for ADF statistics and second position is for p-value. So I'm just plotting both of them over here. I'm just showing the values. So currently our main focus is this p-value. And you might be aware that for hypothesis, generally we consider 0.05 is the threshold for p-value. So here we can reject the null hypothesis and we can conclude that the heart rate time series is stationary in nature. Otherwise, in real-time data, majority of time you will find non-stationary, or there will be a specific trend in data for non-stationarity. But with this value, we are simply rejecting the null hypothesis and we are concluding that heart rate time series is stationary in nature and its statistical properties are not changing over time. So based on this, we can quickly state that for this particular patient, there is like no strong fluctuations available in observations. So he may be more in like a stable condition. But this will not be the case in all time. Sometimes you will have patients that have very high fluctuations in their readings. So at that time, a different type of model may be required for prediction. Currently in this data we have stationarity and there is like no sharp fluctuations in our data, considering very low p-value over here. So we can consider that this is good sign for patient stability and we can predict this heart rate by using ARIMA model. ARIMA model or ARMA model, there are two most commonly used model in your time series forecasting, and they basically help you to evaluate how your continuous time observations are fluctuating over time and how we can track them to forecast in a specific sequence. Like maybe we can forecast for next 10 minutes, for 15 minutes. Sometimes if your model is like very fine, it can even forecast for next 1 hour or even for a day. So in advance, you can predict how patient health may go with time. So if you have a long-term data, a well-trained model on that, you can deploy that somewhere in patient analysis, and it can help you to predict whether patient heart rate will be stable for the time, or it may rise with time, or it may fall with time, so that timely interventions can be taken by the doctors. So for that ARIMA model we are using here. ARIMA in technical words, the full form stands for autoregressive integrated moving average models. But currently we'll call it just ARIMA model because all of you might be beginners in this. So you can just refer to this information later for detailed structure of ARIMA model. But I have just given you a quick idea that why we are going to use this here. So I'll be writing here ARIMA model. And basically when your data is stationary in nature, we call it ARMA model also, because integrated option that we have in ARIMA, that is not required in case of stationary data. Integration option is required when you have non-stationarity in data. So the basic model generally is ARMA model, and we will be deploying this one right now. Later on, by just changing few parameters of ARMA model, you can deploy ARIMA model also. So currently both of them appear same. ARMA and ARIMA, they will both appear same because we don't have very high fluctuations in our data. So this will be like a base model we are deploying. But in future, maybe in some advanced analytics sessions, you can understand that how for highly non-stationary data, how ARIMA model parameters can be updated in future. So what I'll do here is I'm just writing ARIMA modeling for patient heart rate forecasting. That is the next main task we are going to do further. And for this, I'll first prepare my time series data. I'm just getting it ready with my 15-minute average that we have in our data. So this time series data I'm calling here again. This contains all 7 month, I think 7 day data, 1 week data we have here. So this one I'm calculating first. Let me just show you. Okay, this stationarity check you might have not executed. I'm sharing it here. Execute this and let me know if you are done with this. I'll wait for responses in the chat box. When you are done with this, then I'll proceed further. Let me know in the chat box when you are done up to this. If I need to wait for anyone, then also let me know. Okay, you are not seeing code in CodeShare. It is here only. Which code you are not able to see? Nothing, or just last one you are not able to see? Because it is right now available here on screen itself. You can just refresh it once if it works. Let me know. It last one. Okay, let me just check. This is also available. I can see this here. Let me know if others can see it here. I have also pasted it again also. Check if it works now. Okay, great. So now I'm just fitting this ARMA model and I'll call it from stats model repository again. I'll go to time series analysis and from here I'll call ARIMA model repository further and I'll import ARIMA that is saved with this name in your Python platform. And then I'll just deploy this ARMA model. I'll call here ARIMA and I'll pass here my time series data. If you remember TS, this is my time series data that I'm passing here. And inside this, I'll pass order of my model, that is 101. This is the basic model, ARMA model we are creating. Here, there are 3 parameters in your ARMA model right now I'm passing. They basically help us to make judgment over the stationarity of your data to ensure that it is predicted well. So in technical terms, these 3 terminologies are represented with P, D, and Q. These are 3 variables that we have in sorry, this order sequence, where P indicates your periodicity terms first, and similarly this is representing your autoregressive order, main order. So that keeps a track of past number of observations. so that if past observations have a direct impact on current observation, that trend this first p value will manage. Then second, this one, this zero, that is represented by d. This d is your differencing order over here. This represents that if we have any kind of non-stationarity in your data, then we need to conduct some specific mathematical evaluations behind to remove some unwanted trends, etc., so that we can achieve a stationarity available over here. Currently, we are keeping this zero because our data is already stationary. But if our data is non-stationary, means by default, if it is not stationary, then we can update a value here also, like 1, 2, 3, some values we can test over here also. Then last value, I'm keeping 1, that is for Q, that is for moving average order. This basically helps us to make evaluation based on past forecasting error, because in time series we are forecasting continuously. As live data is coming, we are trying to forecast for the next. So this will keep a track of past mistakes in forecasting. If there are any errors in past mistake, it will just try to minimize them in future. So it will keep on improving its prediction sequence as more and more data is coming, and in future it may be predicting better for all the observations for certain category that we are passing. So currently I'm creating this as a very basic model. In future, depending upon how your data is distributed, you may change these values for testing with multiple variations. Like you can have 210, 222, 234. There are multiple combinations that you can try later on. This is the most basic model that I'm creating here right now. So after passing this order information, then I'll write here ARMA fit, and inside this I'll pass ARMA model, and I'll be writing fit for this. And then we are passing summary for this particular model. So this will follow the time series data, because TS I have already passed here. So this TS we have represented here. This data is already contained in our model development. So we are just fitting our ARMA model now on this TS data, and we are just creating a summary of this model, that how it may be working behind. This summary currently will be just based on your mathematical derivation behind your model. So this may not be like a very easy to grasp thing for you, but yes, you can still see summary of your model, and you can present it somewhere in your maybe reports, wherever you need to show your outcomes. Let me check just if we have some issues with this. Okay, I'll explain this PDQ again. Let me just check if I have some typo here first. So I'm getting, okay, this one requires a dot because we are taking model from ARIMA. Now we can get this output. These are just some statistical evaluations that it is doing behind. Okay, I'm explaining this PDQ again. Let me just put them one by one again. So these ARIMA models are basically defined with 3 parameters, P, D, and Q, for which we generally pass some numerical values. The D values are generally integer values. P and Q values can be float and integer, anything. There can be different combinations of these values. First, let us understand which part they are controlling in your model. First part we have is for P, that mainly represents your, technically we call it autoregressive order. This is name given to the P value, autoregressive order. The main function of this P value is to keep a track for past observations that may directly influence current value. So as we are currently making prediction over heart rate, so this P value will ensure that all the past observations of heart rate are on track. It will just keep an eye on them, that how the fluctuations may be going on in that, so that we can just the model can just have an idea about what may happen ahead, because that past track only will help it to understand how the patient is doing right now, whether his heart rate is going normal or there are some special seasonal changes or maybe some trends are going on in that heart rate observation. So P helps to keep a track of past observations that may influence current value. So that is the first task we are doing. Then second thing, we have D value over here. This D value is your differencing order. Technically, we call it differencing order. So this helps you to see the number of times your time series data is required to be differenced for achieving stationarity. Technically, we give this definition. But in simple terms, as a beginner, what you can understand that if your data is not stationary in nature, means if its mean and variance is not constant over time, if they are not constant over time, then we may have to achieve seasonality by applying some manual control in model. And that we apply with the help of this differencing order. So what it will do is it will try to remove trends or seasonality. Technically we call it seasonality also, like some if specific uh, pattern to achieve non-stationarity if it is following. So we just need to remove that to achieve stationarity in your observations. But currently we have observed, like I gave you one stat over here, that our p value right now is less than 0.05, which is threshold of p requirement whenever you conduct statistical analysis. So with this value we can initially assume that our data is stationary in nature. So because it is already stationary in nature, we do not need to compute this intermediate parameter. And when this is 0, then only your ARIMA model is called as ARMA model, because then intermediate, that integrative factor, we do not need to evaluate at that time. Then we keep this value 0 only, because we need not to do any differencing. We need not to conduct any mathematical differencing between fluctuations behind to achieve stationarity over here, because by default our data is stationary in nature. Then the third parameter we have is Q parameter. This technically is named as moving average order. This is name for Q value. And this basically helps you to keep a track of forecast errors in the past. Because when we are dealing with time series data, we assume that your live data is coming and every time it is making prediction for the next sequence. Like maybe if you are doing time series analysis or maybe some pollution parameter, for example. So continuously some data is coming and you are just observing that data, that okay, your dust particles are increasing in this area. You are just observing that trend. So your model is just keeping a track of that trend. It is predicting continuously. Like if currently this value is there, it will predict that okay, for next 5 minutes there may be a rise or fall in your dust particles. So it will just keep on predicting every time. But when your model is at initial stage, there will definitely be some errors also in prediction continuously, as it is getting live data from somewhere, whether it is pollution data, weather data, patient data, any kind of data. If it is predicting over time, it may also make some mistake in between. There may be some errors. We call them past error, because currently it is making prediction. If it has made some mistakes in the past while doing prediction, like maybe the expected value as per prediction are getting difference. Maybe we are having a value of 20 in actual, but the predicted value was 15. So there is a gap between predicted and actual value. So this Q parameter will keep a track of those errors so that your prediction performance can be improved with time. So keep a track of past errors in forecasting. This is its third technique. So when these three things are combined together, means when these values are updated right, then your model may perform better. Currently, we are conducting just a base model analysis. I'm using very basic values, 101. But for advanced modeling, you may have to change these values. You may have to balance them with the fluctuations in your data. You may have to change these values. So as I told you that majority of time this intermediate one is kept as integer value, and these ones can be integers or float. Both are accepted in this case. So accordingly, your model behavior can be improved by adjusting these values. Let me first know if it is clear up to this. Okay, great. So after deploying this particular model, we can see here model summary. I'll not explain this part in detail because since you are not from core engineering background, this will be like a complicated description for you. But yes, this is just a quick observation on what parameters your model may be considering behind, how the observations it may be evaluating, some statistical measures it is finding in between, and these are its own evaluation parameters behind that are working. So all of them are presented here. So if anyone in future wants to do in-depth statistical analysis on that, how your ARMA model is working, that you can evaluate based on these parameters in future. But currently I'm just showing you a quick summary of this model, that this is working on these parameters here, and it will be giving you predictions for the next steps. So what we will do after executing this, like I have executed this particular model, I'll first share this with all of you as well. I'm sharing the stat model code in your code share window. And then I'll use here forecast future heart rate, for example. Because currently we do not have a very huge data. There are very lesser number of observations, like we have only 672 observations. So we will not be able to make very long-term predictions. And also ARMA models are generally used for short-term predictions. So we will predict like for maybe next 15 minutes only. So that short prediction only we will do here. In future, when you design some regressive models, some very heavy models, they may predict for multiple hours also, or sometime for multiple days also. So in order to predict, I'll write here a forecast parameter. I'll make it ARMA fit, and I'm just using forecast option here. And then steps I'm writing is 12. Like for next 12 steps, I'll be predicting here. That could be like with 15-minute interval, it may make next 3 hours. Or you can reduce this also, like maybe considering some lesser number of steps, higher number of steps, you can change. But generally, we expect that you do it for short term at initial level. So maybe with 15-minute interval, like currently our data is with 15-minute sequence. So next 12 steps on that, we are trying to predict with this forecast. So I'll just run, let me just check. Okay, I have just made a typo over here. It is forecast. So I'll just run this, and the forecast is done, and we can now plot this. I'll just quickly plot this. Although currently it is not like your model will be very accurate, because we have very small data set. Generally, we need very heavy data set when we are building these kind of models. But yes, you can just understand how the entire execution may be going on. So in the last step, I'll just plot this forecast. And here I'll write plot figure, and I'll write figure size with 10,4. Then I'll write here plot TS label, that is your observed values, because in TS variable you already have your observed time series value. Then I have the next forecast that I have stored here. So what values will be there for this heart rate, that is stored in forecast right now. And I'll write for this label as ARMA forecast. And for this, I'll decide maybe in red color they will be observed. So this will get a by default color that is generally blue in your Python. Generally, it takes blue color for basic plotting. And the other one, that is your predicted value, I'm putting it in red color so that at least we can identify, because that will be a very small notch, because just 12 steps only we are predicting. So that will be a very small notch. But still, we are just trying to observe what kind of pattern it may predict further. So I'm just putting here a title, based heart rate forecast, and ultimately we will just try to show this plot. So I'll just run this and we can see this red notch. You can observe here, currently this is being predicted, because I told you that this is a very minute data and very small notch you will see over here. Very small prediction we are doing from here, which since number of observations are already very less. So, but this kind of outcome it is showing right now, that it will stay in this trend based on the past data that we are having from this. I'm sharing this with all of you. You can just create this kind of plot. Later on, maybe you can use it with some heavy data, and based on that, you can use your interpretations. So final step I can add here, clinical interpretation. Maybe if you want to put in this, integrate in this sometime. So if forecast dot mean is greater than TS dot mean plus 2 into TS dot STD. So this is mathematically we are trying to evaluate it, that if the forecast mean is in a range higher than this, that is time series mean plus 2 multiplied by time series standard deviation. In that case, we will print the alert. So we will write alert, sustained elevated heart rate predicted. So in that case, we will say that some critical event is predicted for patient health. Otherwise, we will say that forecast within normal variability. So these two conditions we can deploy. So we are just observing. Currently, it is saying that everything is in normal condition. So as we have already observed that our data set was stationary in nature, so there were no major like peaks available in the current form of data. So it states that after prediction, it is predicting that everything is normal. There is no any peak variability is not found in data. But if there are any peaks, like something like this, if it finds something like this, then it may state the other way also, that there is an alert and we need to take some immediate action for the patient health. So that way also we can observe this. So I'm sharing this last portion also in your chat box. Execute this and let me know when you are done. I'll wait for responses in the chat box. Let me know when this all is done, then I'll just one time explain everything from the top. Just a quick overview of whatever we have done. I hope others are also able to do up to this. So I'll just get back on the top portion and I'll just explain everything once again. First, we have just imported essential libraries that we are doing same from past few days. So you already know these libraries. Then we have just brought up the data over here in df variable, that is with the help of read CSV function available in pandas library. After this, we have analyzed quick information about this data, and here we observed that timestamp is currently in object format. But when we are doing time series analysis, this timestamp is very important variable and we need this in date time format. So we did a next step, we converted this timestamp into date time format, and in that we can observe now in info function that this timestamp is now available as date time format directly. So in the next step, I just converted this timestamp into a index variable so that it doesn't appear like normal column in our data, rather it appears more like a index column. So this is coming at this level automatically, and this is appearing like observation index now. Then further step we had for patient ID analysis. We just tried to observe that how many patient data is incorporated in this particular data. So currently it shows 10 different patients, and for each patient we have 2016 observations. And for this, we further made a decision that because we are doing time series analysis, so we cannot predict for multiple patients at a time, but this model we will use for one patient right now, and we will try to analyze condition of only one patient with this. So I just separated patient ID 1 from my main data, and I saved it inside patient underscore df variable. And then after this, we are doing all analysis on this single patient now. In the next step, I did a 15-minute averaging on patient data because currently your data was with 5-minute sample. But then I just explained to you that with your real-time data, generally very fast sampling may not suggest very strong change in your data, so we generally take average. So that could be 15-minute average, 1 hour average, 30-minute average. Different cases may happen in different domains. So currently I'm just taking a 15-minute average from my heart rate data, and we are just resampling this to get the mean values in your new data. So now you can observe here the 15-minute entry sequences, and for that the heart rate is evaluated one by one. After this, I have just plotted this 15-minute average data just to see how heart rate observations are present for this patient right now. Then we moved forward to trend and seasonality analysis, which is very important in case of time series data, just to observe whether our data is stationary in nature or not. So for this, I calculated two types of statistical observations that were rolling mean and standard deviation, for which I have shown you that how this rolling mean works. We keep on shifting window to cover entire data, and it keeps on calculating mean and standard deviation while shifting that window one by one. So here with a window size of 8 samples we have used, and we are calculating this rolling mean and standard deviation. After that, I have just plotted both of them against original data. So this blue one is showing original heart rate, orange one was showing your rolling mean calculated from this original heart rate, and then this green one is showing rolling standard deviation calculated from original heart rate. Then I conducted a statistical test to ensure whether our data is seasonal in nature or not, or stationarity mainly we are taking. So for that, I conducted here Ed Fuller test, and in which we are evaluating two parameters, out of which I'm focusing on p-value right now. So p-value threshold, if you remember, it is generally 0.05. If we need less than that value is considered as for this particular case, that will be considered as stationary data, and greater than 0.05 will be considered as non-stationary data. So with this value, we can here assume that currently our data set is stationary in nature. So for that, we decided to use ARIMA model in its base format, that is generally known as ARMA model. So then what we did is, for forecasting heart rate for single patient with the available data, we used this time series data variable where we have kept all our 15-minute observations for heart rate, and then I utilized this to fit my ARMA model. And here I just called my ARMA model from stats model library, And then I just fitted it over 101 order that I have explained here, that because this is a very basic model, so we are keeping value 101 only. Later on you can change these values with different ranks and you can see how your model performs. So for keeping a track of past observations and the forecast errors, as well as if there is stationarity or non-stationarity in your data, based on all these observations only these values we will set, and we will just fit it over our time series data. So after fitting, we are just getting a summary of this model, that is just to see how it may be evaluating things behind that summary we have created. And then we ultimately try to forecast next 12 steps by using this ARMA model, the one that we have fitted already. We just try to forecast next 12 steps with it. That could be next 3 hours mainly, because we are using 15-minute average right now. So ultimately, we just plotted those forecasts and we could observe here this last red line, only very small portion we predicted. So that one we can observe by the end over here. And this as a clinical prediction, we took that currently patient is in stable condition and there is no major variability in data. But if there would be any consequences of that, so alert can be generated corresponding to that fluctuation in data. So this is the entire case study we have evaluated till now. Let me know if everything is clear up to this. Okay, great. I hope for others also this is good up to this. So today we'll just stop here, and because our case study is done for now and you can spare some time maybe for your practice later on now. Tomorrow will be last day of this workshop, and there also we have a lot of new things to learn again. So we'll meet again tomorrow at 6. But if you have any queries, let me know before we wind up this session. You can put in the chat box quickly. I hope everything is fine up to this.
Ma'am, can I ask a question now?
Yes, please.
This forecasting is done on time values. I mean, the heart numerical values like heart rate.
Right.
Can we also forecast on the categorical value? I mean,
Time series is done on continuous variable.
it's
Time
only
series
on
analysis,
continuous.
yes, that goes with continuous variable.
Okay, because we say one of the column is patient condition, normal
Yes,
or
yes.
abnormal.
That
So
was
it's
just a detailed data we had, but then I picked only continuous variable for forecasting out of that.
okay. So we can't use to predict it whether the patient condition will be normal or bad, something
So that
categorical.
will be normal classification in that case. So for that, you can use normal classification modeling that we have done day, I think
Okay,
on
yeah.
fourth day. Yes.
Fine. Okay. All right, ma'am. Thank you.
Okay. Any other queries, please? Okay, so if we don't have any further queries, we can wind up the session for now, and we'll meet again tomorrow for a few more important discussions.